In this video, we're going to go over how to derive the derivatives for some of the inverse trig functions so that you always have a plan B on your test. Let's jump in. In this video, I'm just going to show you how to find the derivative for inverse sine and inverse tangent, since the other ones are pretty similar to these actually. To find these derivatives, we're going to also need this function. Basically, what this function says is that if you have two functions, f and g, and they happen to be inverses of one another, so that's important. This is only true when f and g are inverses, then this equation is also true. In other words, you can find the derivative of one using the derivative of the other. I've already covered in another video why exactly this function is true, so I'm not going to go over that here. I'm just going to use it. The basic idea, if we believe this function, again, for inverse functions, it's only true when f and g are inverses, is that we can use the derivative of sine of x to figure out the derivative of arc sine of x, or inverse sine. One other quick comment is that hopefully you've seen this notation and you're aware of this. Sine inverse of x is arc sine. So whenever you're dealing with any of the trig inverses, this symbol right here means the inverse. You can just replace that with arc. I prefer to use arc. I actually kind of hate this notation, but you will often see this in class and also on your calculator. So this is like sine to the -1 is official notation. The problem with that a lot of students run into, and this is kind of the reason I hate it, is that it makes it look like this is what it is, but that's not true. Inverse sine using this notation is not 1 over sine. Remember, 1 over sine is cosecant. So a lot of students make this mistake because honestly, it's using the same notation. It looks like it's a negative exponent when it's really not. So that's why I do not like using this notation, but just as an FYI, you might see that. You probably will see it in your class. I always try to use this notation because it's unambiguous, or you can't really confuse it for the other thing, or at least it's less likely. So that's why I like to use arc sine. But anyway, how would we do this problem? The first thing to identify is what is g and what is f. So if we just do some kind of basic pattern matching here, hopefully it's clear that g is arc sine. I'm just going to write that. Actually I'll write it like this. G of x is equal to arc sine, which is what we're trying to find the derivative of. And then apparently this should equal 1 over f. Remember, f has to be then the inverse of g. That's the requirement for this equation to be true. So hopefully it's clear that f of x would just equal the inverse of inverse sine, which is just sine. And think about it, we need to know what the derivative of f is here. We know how to find that. In fact, that's the whole reason we're using this equation to begin with, because we actually already know the derivatives of the normal trig functions. We're just trying to use those to find the derivatives of their inverses. So here, f prime of x, if you remember, is cosine of x. So if I just blindly use this formula in this case with this value of g of x, this value of f of x, hopefully it's clear that I'll get 1 over cosine of g of x, which is just arc sine of x. So there you go. This is the derivative of arc sine of x, 1 over cosine of arc sine of x. Now, this is usually not the formula that we leave it in. Even though this is completely true, we generally try to simplify it. The question is, how do we simplify it? So let's actually take a step back and think about what the denominator here is actually saying. We have a trig function on the outside, and then we have an inverse trig function on the inside. Now, think about the inputs and outputs of trig functions and their inverse trig functions. For a normal trig function, the input is always an angle, and the output is always a ratio of side lengths. Think SOHCAHTOA, for example. Whereas for an inverse trig function, the opposite is true because it's inverted. The input is a ratio of side lengths, so like in this case, x would be a ratio of side lengths, and the output is an angle. So if you think about this, think about those two facts, and then think about the composition of functions here. If I plug in a ratio of side lengths for x, I will get an angle out from arc sine, and then I'm going to take that angle and plug it into cosine. So basically, I'm going to plug it, and then out of cosine, I'm going to get a ratio of side lengths. So basically, through this composition of functions, I'm going to plug in a ratio of side lengths and get out another ratio of side lengths, if you want to think of it like that. And that can actually help us here because whenever that's true, whenever you start off with one ratio of side lengths and you end up with another, there's a special property you can do that you generally learn in pre-calculus to figure this out symbolically. So how does that work? Basically, you can see what I'm already doing here. I'm going to set the inner function to be equal to theta, and I'll do that in a different color. So I'm going to set this inner function to be theta, and then let's think about how we can use that to our advantage. So if I come over here, what I'm going to do is I'm going to say that theta is equal to arc sine of x, which hopefully it's clear that if this is true, then x would equal sine of theta. And if sine of theta is equal to x, remember, what does sine represent? It represents the ratio of sides between the opposite side and the hypotenuse. So you can actually instead think about it like sine of theta equals x over 1, where x is the opposite side and 1 is the hypotenuse in an actual triangle. Also, just to be clear, you could have called it 2x over 2 or 1,000,000x or 100x over 100, and the ratio would still have been true. It's just that the simplest one to look at is x over 1. But this technique would still work using anything as long as the ratio does turn out to be x. It's just that it would be a lot more work for you, so there's no reason to do it. Now, if this is true, let's actually draw the situation to kind of understand what we're dealing with. We're dealing with a right triangle, apparently, where if this is the theta value, and let's say this is 90, because remember, the trig functions are only true for right triangles, then the opposite side we can think of as x, and the hypotenuse we can think of as 1. Now, I don't know if anything in particular jumps out at you, but hopefully it's clear here that if this is really a right triangle, and we know two sides, we can actually figure out the other side. It's equal to, in this case, square root of the hypotenuse squared minus the other leg squared. So that's going to be the other side of this. And again, if you want to verify that, try that out for yourself just to confirm that you get the right answer. If you use the Pythagorean theorem, we just use the Pythagorean theorem in reverse. If you use the Pythagorean to square this and add them, you will get this thing squared. Now, think about what our actual goal is here. Our goal is to figure out cosine of theta, right? Because that's what we need. We need arc sine of x is theta based on our initial decision. So if we can figure out cosine of theta, then we're good. What is cosine of theta based on this visual? Remember, cosine is adjacent over hypotenuse. Adjacent side is square root of 1 minus x squared. And then the hypotenuse is 1. Therefore, cosine of theta is equal to just the square root of 1 minus x squared. That's what we just figured out. We started off with one ratio, x, and then we got out another ratio, square root of 1 minus x squared. But these are both ratios of side lengths. And you can use this. You can use this up above. So if we plug in, if we replace this entire cosine of theta with that, hopefully it's clear that we would get 1 over square root of 1 minus x squared, and that is the correct answer. That is the derivative of arc sine, 1 over square root of 1 minus x squared. To find the derivative of arc tangent of x, you would follow almost an identical process. We decide what our g, and again, this formula, remember, is only true if they're really inverses, so we're going to say that g of x is equal to arc tangent now. And we'll say that f of x is therefore equal to the inverse of that, which is just tangent. And then we're going to say that f prime, the derivative of f, is going to be equal to, if you remember your trig derivatives, secant squared of x. And otherwise, we can do basically the same thing. So this thing will equal, think about it, it'll be 1 divided by f prime, so secant squared, evaluated at the inner function, or evaluated at g, which is just arctan of x. And I won't explain this in too much detail, but we can basically use the same process as before. We have an inverse function on the inside, an inverse trig function on the inside, and then a regular trig function on the outside. So as that composition of functions, we plug in a ratio of side lengths, and we get out a different ratio of side lengths. So we can do the same technique, basically. We can say that this thing is equal to theta. If we come over here, how would that go? Theta is equal to arctan. So I'm basically going through the exact same process almost, with minor tweaks. So now it's going to be tangent of theta is equal to x, and you can think of it like x over 1 if you want, which you should actually here. Now remember, tangent is opposite over hypotenuse, or sorry, that's sine. Top tangent is opposite over adjacent, TOA, in SOHCAHTOA. So x, if this is theta, the opposite side would be x, the adjacent side would be 1. The question is, what is the hypotenuse now? We can figure that out with the Pythagorean theorem. It has to be square root of 1 plus x squared. And if I take that, remember what we're trying to find is secant. What is secant? Secant is 1 over theta. So we're trying to find, actually, if you want to think of it like this, secant of theta, the whole thing squared. Secant of theta is 1 over hypotenuse, or sorry, 1 over cosine, I mean, and then cosine is the adjacent over the hypotenuse. So hopefully it makes sense that secant is the reciprocal of cosine, which is hypotenuse over adjacent. So in other words, this is going to be the square root of 1 plus x squared, and then the whole thing squared. And again, that's different. We didn't have the square on the outside in the last step because the derivative of sine is just cosine, not cosine squared. Here, the derivative of tangent is secant squared, though, which is why that's why we had this extra squaring that we didn't have before. But basically, if we plug this in, hopefully it's clear that the square and the square root cancel each other out, and basically secant of theta squared, the whole denominator, is equal to just 1 plus x squared. So this should just equal 1 over 1 plus x squared. And that is the derivative of arctangent. 1 over 1 plus x squared. The other four are very similar to this. Secant and cosecant are a little trickier because you'll have an x on the outside and you'll end up with an absolute value. So it gets a little bit uglier with those. But basically, besides that minor point, you follow the exact same process to get all the other inverse trig derivatives. So this should always be a backup plan. Again, I don't recommend using this as plan A. Plan A should still be to rote memorize the inverse trig derivatives, and there are special ways that you can make that easier on yourself, which I cover in other videos. But it is, I think, also very important to be aware of this process as a plan B in case you forget them on a test. Then you can basically go through maybe a couple minutes of work to rederive it. And I think that's worth it. So there you go. Hopefully all that makes sense. If you have any questions, be sure to leave them in the comments. Otherwise, I'll catch you next time. See you.